for these scaling functions how multi-resolution analysis is possible. In order to agree with our intuitive idea of a scale or resolution, we formulate the basic requirement of multi-resolution analysis. By requiring a nesting of spanned spaces are given by from minus infinite it is extending, then v minus 3 is a subset of v minus 2, subset of v minus 1, subset of v naught up to so on L square. Or simply the entire equation can be notated by a simple expression as Vj subset of Vj plus 1 for all j belonging to Z with the conditions given. At the end of this L square, all the functions are going to be embedded into this space, so that V infinite equal to L square, where we started at minus infinite. So up to that, how many subsets are there? V minus infinite equal to 0 set. The space that contains high resolution signals will contain those of lower resolution also. Because of the definition of Vj, the spaces have to satisfy a natural scaling condition. That means, suppose f of t belonging to Vj, you can frame f of 2t which is belonging to Vj plus 1, or if you know f of 2t, you can form the f of t. This means this is the higher resolution, this is the lower resolution, this is the higher resolution. So, higher resolutions can be obtained from the lower resolution, which ensures elements in a space are simply scaled version of the elements in the next space, the name itself. The nesting of the spaces of phi of 2 power jt minus k denoted by Vj. See this diagram, nested vector spaces spanned by scaling functions. The first one we form it a V naught, then along with some other translated versions of these functions going to be forming V1. That means V1 is a superset of V naught or V naught is a subset of V1. Similarly, some more translations from the V1 attain V2. Some more translations from V2 attain V1. This is the nested vector spaces spanned by the scaling functions. Similar way, this was a simple notation V0, V1 and V2. For understanding purpose, the color difference going to be given here. Then phi of t scaling function is equivalent to summation n h of n root 2 phi of 2t minus n belonging to Z. Almost this expression looks like convolution principle. That means one function going to be kept constant, the other going to be translated. By this way, like a filter, if you know the coefficients, you are able to design a filter. Here, if you know the coefficients, you are able to find out the scaling functions or coefficients relevant to scaling function. This recursive equation is fundamental to the theory of scaling functions and is in some ways analogous to the differential equation with coefficients h of n and solution phi of t. That means you are finding a solution to phi of t in terms of h of n. This can be analogous to differential equation. H of n is a discrete notation. If you go with either Z domain or Laplace domain, you are going to observe that these are going to be this equation almost equal to the differential equation.